Right, so we're looking at pressure in this little clip, and we need to define it first of all as the force per unit area. So in symbols that turns out to be P for pressure, F for force, divided by area, symbol capital A. This gives us the units for pressure as newtons per square metre, because we're dividing newtons for force by square meters for area. And this is known as a Pascal. So 1 Pascal is the same as a Newton per square meter. Now there are many applications of this equation to real life situations. And so we're going to look at that next. If you consider though your weight force as a starting point, when you're standing up, your entire weight force is acting through your feet, and your feet have a very small surface area compared to, say, your whole body. So if you were to lie down on the ground, the area would be much greater, and that's why you feel less pressure acting on you when you're lying down as compared to when you're standing up. So the smaller the area, the smaller the pressure will be for the same given force. So here's an example of that same idea. Calculate the pressure exerted by the same 200 kilogram box when sitting in the two positions shown. Now we look at the box and we see it's 4 meters high, 2 meters across, and it says here 0.1 meter in terms of the other dimension, which you can't really see, but it's 0.1 meter deep. So in the first position, we'll call this position 1 here, and this can be position 2. In the first position, of course, we have a particular area exerted on the floor along this side here. And that area will be, we'll call that A1. We can calculate that to be 2 meters times 0.1 meters, so that gives us 0.2 square meters. And then we can calculate the pressure as the force, or we'll call it P1, the force acting over that area A1. The question is, what is the force? Well, in this case, of course, we've been given the mass 200 kilograms, so we need to change that into a weight force, and we can do that by multiplying it by 10, assuming we're on Earth. So F subscript W for weight force is 200 times 10, that gives us 2,000 newtons. So now we can calculate the pressure P1 as equal to FW over the area A1, and we plug that in, we get 2,000 divided by 0.2, so we get 10,000 Pascal. Now we can write that as 10 kilopascal. And now we can do the same thing with area 2. In this case, area 2 will be equal to this area here, which will be 4 times 0.1. 4 times 0.1, and that gives us 0.4 square meters. I'll just take away some of this stuff here. Wait a second. So now we can calculate the pressure P2 as equal to the weight force FW over the area A2. The weight force is still 2,000 newtons, but the area, of course, is 0.4 now, and that gives us 5 kilopascals, or 5,000 pascals, which is half as much as when the box was standing upright. Some other examples of reducing pressure and why it might be useful. If you consider a four-wheel drive vehicle that wants to be able to move across soft surfaces like sand and mud, then to achieve this, of course, the surface area of the tyres should be as large as possible, and hence most of those vehicles have fairly wide tyres. They certainly wouldn't be very useful if they were narrow. Other examples, snowshoes or skis. They assist people moving over soft snow. Now, here are a couple of things to consider. If you want to describe how pressure is related to hammering nails, all you have to think about is how difficult it is to hit a nail into a piece of wood if the nail is not sharp. If the nail is blunt, say you had a nail like this, it would be very hard to actually hit that nail into the wood. Whereas if you had a nail with a pointy end, kind of hard to draw a pointy end on this, but anyway, a very pointy end, the surface area at the tip would be very small, and hence you wouldn't need much force to drive the nail in. Another example is comfortable footwear as opposed to uncomfortable footwear. If you consider wearing rugby boots with sprigs and running across concrete, the reason it's uncomfortable for your feet is because the surface area is quite small, the surface area being the area of the sprigs combined, acting on your feet. Another example would be women's footwear. High heel shoes, for example, are not particularly comfortable for the same reason. They don't have much surface area to carry the weight of the person wearing them. Pressure is also related to things like bullets and dolphins and racing cars, anything that's streamlined. In this case, we're reducing the total force acting on the object by having a profile that allows for air resistance or water resistance to move smoothly around the object rather than smacking straight into it, which would be the case if we had a flat surface. And this brings us on to atmospheric pressure. This is produced by the weight of the air atmosphere pushing down on us. So at sea level, atmospheric pressure is equal to about 100,000 Pascal. That's equivalent to 100,000 newtons per square metre acting on every part of our bodies, which we don't usually notice. The only time you do notice it is when you change your altitude rapidly. For example, you take off in an aeroplane, or perhaps you dive underwater. So when you dive underwater, you are actually adding more weight on top of you, all the weight of the water plus the weight of the atmosphere. For example, if you go 10 meters deep in the water, that's another entire 100,000 pascals added on top of the atmospheric pressure. So you'd be experiencing 200,000 pascal when you're 10 meters deep. When you go up in an aeroplane, the opposite is happening. Basically, there's less pressure outside, and so your eardrums are bulging outwards, and you feel a bit of pain until you sort of equalize the pressure by swallowing and drawing air inside your body, which has the same pressure, therefore equalizing things. Just remember in class sometime during this cycle to bring along an empty aluminium drink can, then we can test out the effects of atmospheric pressure.